Are you going to do an intro or should I just start?
Yeah, let's start with the fourth lecture.
Thank you for that kind and thoughtful introduction. Okay, so last time you need to hear from me, good news. I'm going to tell you about the dark energy from the Dark Energy Spectroscopic Instrument. I am co-spokesperson for the Dark Energy Spectroscopic Instrument, so I am contractually obliged to show this slide. If I do not show this slide, I should be taken out and shot, because I am the person, that's probably a bit too extreme, but I am the person that has to tell people off if they don't include this slide in their talk. And it's a serious slide to include because DESI is a big collaboration. It involves a lot of money, and where there's money, there has to be credit. And the credit here goes to a large number of different foundations, government agencies, and so on, that have basically thought DESI is a good enough thing to do, that they have put their money where their mouth is and given us the support that we need. There is also a large number of people from 72 different institutions around this world doing this international project. DESI in a nutshell. DESI is a multi-object spectrograph. The cosmological advancement happens because of engineers. Engineers design better and better experiments, those better and better equipment to do experiments. And the driving piece of equipment for a galaxy redshift survey is the multi-object spectrograph. This is basically the instrument that sits for the DESI at the top end of the male telescope, and it can use little micromotor robots to position 5,000 fibers at known locations on the focal plane of the telescope, such that if you point the telescope at one patch of the sky and you have a set 5,000 list of objects you want to observe, these little motors can place fibers at the known locations of those objects. These are 50-meter fibers. They basically take the light down from the top end through to the clean room by the side of DESI, where they are fed, the light is fed into spectrographs, and you get spectra out. DESI is an amazing experiment because it is 20 times faster than what went before. The previous best multi-object spectrograph was on the Sloan telescope. It enabled the Sloan Digital Sky Survey, a great experiment, but DESI is 20 times better. That comes from having 5 times the number of fibers and 4 times the collecting area. This DESI is on a 4-meter telescope, whereas the Sloan telescope was a 2.5-meter diameter telescope. It is good to be living in times where we are doing experiments that are 20 times better than has gone before. If you look at experimental advancements, a factor of 20 is an incredible progression. That means, just to put it in numbers, that DOS, for example, took 5 years to complete. 5 years of going out to the telescope every night, changing plates over, getting new observations. DESI can do that in 3 months. It's a little bit disheartening, but also very good. DESI has now released its first set of public data, 5 million galaxy redshifts. That was released in March this year. The final area will actually, I think, be slightly more now than 14,000 square degrees, and we will have more than 50 million redshifts, because amazingly and possibly uniquely for a recent cosmology experiment, DESI is ahead of schedule. Visually, let's have a look. This is SDSS. This is 7 months of DESI. So this is what I mean about basically, I spent 5 years of my life worrying about SDSS. DESI comes along, does it all very quickly and easily. And in the first 7 months of operation, DESI has observed more spectra of objects than had been observed in human history previously from everything combined. So it's a phenomenal bit of kit and a phenomenal experiment. So as with every project, we have data releases. There are still some analyses that we are doing and that people out there are doing on the public data for data release 1. Data release 1 contains, as I said, around 14 million galaxy, around 5.7 million galaxy redshifts. But the team is now analyzing data release 2. This contains 14.3 million galaxy redshifts, and we recently released the Baryon acoustic oscillation results from these data. And our data is split into different subcategories of galaxies. We have the bright galaxy survey at low redshift, we have luminous red galaxies, emission line galaxies, and quasars basically going out in redshift. And the reason we split the galaxy survey into these chunks is that as well as taking the spectroscopic data, we need to know where to put these fibers on objects. So we need target catalogs. Those target catalogs come from previous imaging data, and basically we can cut that imaging data in different ways to select particular types of galaxies and to give those galaxies particular number density distributions in redshift. So here's an example, here's a plot of the data release 1 footprint that were the data that we publicly released in March. And you can see how DESI survey is built up. Each one of these little circles is a pointing of the telescope on the sky. Each one would contain 5,000 spectra, not exactly 5,000 galaxies, because we need to put spectra on the sky for background subtraction. We also observe stars for calibration purposes and so on. But around 5,000 spectra from each one of these circles, and we're doing multiple passes on the sky. So the color here is for different regions compared to the fraction of the final 5 passes that we will have on this sample. And we prioritized building up depth before area. So, but it still has to be observed efficiently. So we see, basically we observed where we could in these red regions rather than these blue regions. Do I need to unplug and plug back in again? Yeah. Count to 5 slowly.
Yeah. 1, 2, 3, 4, 5.
Plug back in.
Usually it doesn't happen again once you replug.
Okay. Okay. And then data release 2, which is the data we're analyzing now, you can see that we've filled in more of the area on the sky with the full passes. So we have full depth in a larger area. We actually have a far cleaner and better window function in terms of the patch of the sky that we have observed. As well as these what we call direct traces of galaxies, where we are using one spectra to get one redshift of a galaxy, we also use the Lyman alpha forest to look at absorption features. You've had a series of lectures on this. I'm not going to go into this in any detail, but this is one of the great things that DESI can do to look at higher redshift. And in terms of the value of a spectrum, and we factor this into our target priorities, a Lyman alpha forest quasar is worth a lot more to us than one of the direct tracer galaxies, because this gives us information about the structure all along the line of sight to the quasar, compared to just having one point in a density field. And so we really prioritize these observations. There's only a relatively small number of quasars that we can use for this. Okay. Okay, so from all of these different direct tracer samples and from the Lyman alpha forest, we can measure the BAO signal, the baryon acoustic oscillations, and from that make cosmological inferences. As is common with experiments these days, we adopted a blinding procedure. So, and I think it's valid as scientists, we should be worried about confirmation bias. Confirmation bias is this idea that from an experiment, you tend to get out what you expect to get out. It doesn't have to be because you've done something nefarious. You don't have to have done something really wrong to do this. It could just be as simple as you debugged your code until you got the answer you expected out, and you stopped there and didn't debug your code anymore, right? Everybody does that, but actually it results in a confirmation bias where it's slightly more likely that your code will give you what you expect than find some interesting thing that's different from it. The other good thing about doing blinding is that you can have the 300 people in the world that are most interested to see what the result is. You can get them together in a room and you can unblind and everybody can go, oh, because they see for the first time the answer from the project that they've been working on for many, many years. And that is really exciting. And I know a lot of people are not sure whether blinding is important or not. But my answer to that would be just for having that situation where you unblind en masse, it is worth doing because it is a really great bonding experience and it is a really wonderful time. Okay. All right. As was done by the person sat here, we did a lot of robustness checks against different types of the analysis choices. Different data vectors, different ways of modeling, different days of getting systematics out of the data, different splits of the data. Every experiment has to do this kind of thing. You have to say, basically, it's a test that at every stage of the analysis, you did sensible things. And that the result is not really sensitive to those choices that you made. How you split the data, how you constructed the model, how you extracted the BAO from the full signal. You want your result to be independent of these choices. And so you will find in the literature big tables or plots like this showing how the end result changes with all of these choices. And hopefully, as we did, showing that it doesn't change with those choices. And we did this for the Lyman alpha forest and for galaxies as well. So here are the BAO measurements. You should be happy to live in an era where people can show plots like this. Because 20 years ago, we were looking at a 3 sigma detection of BAO in a single data sample. And now we have huge sigma detections in multiple data samples as a function of redshift. There's been a huge transition in the field where rather than just detecting BAO, we're going to the stage of using BAO as a precision tool to understand the expansion of the universe. Yeah, and this is wonderful. This is a factor of 20 better than, this is the result of having an experiment that's a factor of 20 better than previous experiments. So each one of these points gives us a measurement of the co-moving sound horizon at recombination, normalized by the projection to the redshifts of those galaxies. If we were just looking at redshift 0, our BAO measurements would measure H0 RD. This you can think of as being the delta Z of the co-moving sound horizon at recombination that we talked about yesterday. Because these are all at redshifts slightly higher than 0, if we look at them at flat lambda CDM models, as I showed yesterday, you have a Friedmann equation that only depends on the matter density. You also have a constraint, a degenerate constraint on the matter density. So the core measurement from BAO at any redshift is a degeneracy in omega m and H0 RD, which is basically just telling you in this parameter set, in this set of models of flat lambda CDM models with the parameters of those models, this is what is being constrained by having one location of the BAO feature. Because all of these different data samples basically tests a different set of redshifts, the slope of this degeneracy changes as a function of redshift. So you will see that at different redshifts, we have different degeneracy directions. And when you put them together, you can constrain both the fundamental position of the BAO feature at redshift 0 and the evolution as parameterized in a flat lambda CDM set of models by omega m. And this is the power of having BAO measurements as a function of redshift, is that you get these different degeneracies, and that then the end result is basically the set of models that looks like the data at all redshifts. So we're analyzing at the moment the data release 2 sample. This is a plot comparing it to the data release 1 sample. DR1 are in the open circles, DR2 is in the solid circles. This is one of the plots that everyone went ooh to at the collaboration meeting when we unblinded, because it showed basically that the error bars have come down nicely. Points that were anomalous in the sense that they didn't fit a smooth curve through the other points became closer to that smooth curve between the other points. So even without saying it's this particular model or that particular model, nobody expects the distance redshift relationship in the universe to be anything other than smooth. So if you look at your data points and you look at a smooth model, as you go to better and better data, you hope your data points will look more and more like a smooth model. And that is indeed the case. The dashed line here is the Planck best fit lambda CDM model, and the solid line is the DESI DR2 best fit lambda CDM model. And you can see that they start to differ now. Okay. One thing we did differently in DESI DR2 is that at a redshift of around 1.5, we had a new quasar distance ratio measurement, which we didn't include in DR1. So that was one of the big things. Okay. So this is a plot that got everybody really, really excited, because this is a plot comparing now omega m and H naught RD, as I explained, the parameters determined by the BAO, to the predictions from Planck, shown here in pink. And the Planck predictions predict a value of the matter density of around 0.32, whereas DESI prefers a matter density of around or just less than 0.3. This was at 1.9 sigma for DR1, which is shown by the dashed lines, and for DR2, it has increased to 2.3 sigma. There is a big coincidence here, and that is that the DESI BAO data predict a value of the matter density and this H naught RD that lies on the degeneracy that the CMB constrains. And there is no reason for that to be the case necessarily if DESI is finding something different at low redshift to Planck. And what this means is if you take the DESI data and predict theta star for the CMB, the projected position of the first peak in the CMB power spectrum, you find that it agrees almost too well with the value of Planck. So this is what I would call a coincidence that without looking at the CMB, DESI plus lambda CDM predicts the Planck value of theta star, even though it predicts different parameters for lambda CDM. Now, after we'd produced our first set of data, the ACT results came out. And I have not put them on this plot, but ACT actually preferred a higher value of omega m in lambda CDM. So ACT would be even further up this degeneracy here, but a very similar theta star value to Planck. But Planck plus ACT predict a lower value of omega m than either Planck or ACT together. So there's something quite funny going on between Planck and ACT, moving up and down this degeneracy of models that have the same theta star. Okay. So we talked yesterday about how we can measure H naught with BAO plus BBN. This is the DESI value of that H0 measurement. Now we use basically the BBN value of omega B H squared to remove the RD dependence on the x-axis of these plots, turn it into just an H0 measurement. Then you find that DESI plus BBN prefers an H0 of around 68.7 or so. It's slightly higher than the Planck value, but remember the distance ladder is off up here at 73 or so. So it's still way away from solving the Hubble tension. The sigma against the CMB is now 4.5 sigma rather than 5 sigma. It's just basically where you put H0 from either the CMB or BAO plus BBN. So the interesting thing that grabbed a lot of attention is that this difference that we see in lambda CDM parameters between the cosmic microwave background and the DESI data could be explained, if you really had to pick a physical explanation for it, it could be explained by dynamical dark energy. Because dynamical dark energy changes the expansion of the universe, particularly between the low redshift DESI and the high redshift CMB, such that the projection distance is different. And then if you do that, you can bring what is basically the acoustic peaks back into alignment by having a different expansion of the universe between the last scattering surface and low redshift. The way that this works, is that if we look at the dark energy equation of state, we cannot change it or cannot have this effect by looking just at a constant change in the dark energy equation of state. We need a time evolving dark energy equation of state. And if we put this in, for example, using this, what's called the CPL parameterization, then we find that DESI has this weak preference, DESI alone, for W0 WA in this quadrant of the space, but is consistent with lambda CDM by itself. DESI plus CMB pushes you further into this space, and this is where really we're solving this problem of having different matter densities from the CMB or from DESI. And the supernova also push you into this quadrant. This is time for coincidence number 2. Coincidence number 2 is that this degeneracy direction roughly points you towards the lambda CDM solution. So if the universe has been set up with dynamical dark energy, it's been set up with dynamical dark energy such that on average, when we do these experiments, it looks a lot like lambda CDM, which is another reasonably big coincidence. The significance of this preference for dynamical dark energy changes quite a lot depending on which supernova sample you bring in as well. And I'll show that in some plots in a minute. Okay. So here are some plots I'm going to show. They show basically against redshift, the distance ratio, basically how the universe is expanding, how the distance changes as a function of redshift. This is the lambda CMB, lambda CDM as the horizontal line, and then the data points, the DESI data points are here in the solid values. And I'm going to compare this to the supernova data, but now with the data plotted as the supernova data plotted as their distance modulus, basically a change in distance modulus as a function of redshift rather than directly as the distance redshift relationship. So here is the best fit lambda CDM from DESI. And as you can see from the trend of data points, DESI prefers a distance redshift relationship that has a distance that gets gradually smaller as the redshift comes closer to 0. This kind of curve is reasonably consistent with a supernova, but not as consistent as other curves. And so this is why we say lambda CDM is roughly consistent with the DESI data by itself, but the parameters are different from the lambda CDM that is roughly consistent with the CMB. The DESI plus CMB best fit lies between the two, as you might think. What's more interesting is that the supernova best fit looks very different. And that's driven, this is the DES supernova sample, which is the most extreme. That's driven by this low redshift data point here, which is higher than the DESI data. The DESI data are favoring a solution that comes down like this. Constant W doesn't work. The best fit constant W solution can't pick up this change where the supernova is higher here. It can't get enough of a change in the distance redshift relationship to fit the DESI data. But a model that has two parameters can do it. You can have this decrease that DESI favors at higher redshift and this increase that the supernova favors at low redshift. And so this is really the DESI plus CMB plus supernova evidence for dynamical dark energy is driven by the general trend where DESI favors this lower values of the distance redshift relationship as you go to low redshift, and then the supernova really wants this kick up here. This is basically showing the evidence as a function of the supernova sample that you include. DES, which I showed previously, has this kick up at low redshift. Different compilations of supernova have different degrees of this kick up, and particularly the Pantheon sample doesn't have it at all. So it's a little bit weird to have these supernova samples with this big difference at low redshift. They all, it should be said, favor this solution where the best fit goes down and then back up again when combined with DESI and supernova. So if you believe dynamical dark energy as the physical explanation for all of this procedure, you have to have something weird happening in the dark energy component where it starts off relatively weak, it increases and then decreases, reaches a maximum around a redshift of around 0.5, then it decreases to present day. And that is driven, this is the physical density, that is driven by having an equation of state that transitions from a very low value to a higher value at low redshift. And this means it has a phantom crossing where the universe goes through a negative energy state at W of -1 that theorists either love because it gives them a challenge or hate because they don't like these kind of null energy conditions being broken. So in terms of the acceleration, it would have to start off stronger than lambda CDM and end up weaker with lambda CDM. Okay. But as I said, there are some worrying coincidences in this result as well. And I think the exciting thing to me is that we now have something to test against lambda CDM with future experiments. And we have an interesting physical explanation if it does hold up. Okay. You had whole lectures on neutrino masses. I will just give you very quickly the DESI take on neutrino masses. Massive neutrinos change the angular diameter distance to last scattering surface by changing omega m. The CMB is limited by the geometrical degeneracy, this combination of omega m and h in constraining this parameter. But BAO helps to break this degeneracy, and a constraint from BAO on omega m, like the one we have, helps to constrain the neutrino masses. One interesting thing is this upper bound that you get from CMB plus DESI is not bounded by by zero neutrino mass. If you basically extend the equations on neutrino mass so that they work the same way as you might expect as you go to more and more negative neutrino masses, you get better and better fit solutions. And what's happening here is that the neutrino mass, this is all in a lambda CDM context, And having this kind of effect on the power spectrum is equivalent to bringing the omega m's back into more accord between the CMB and DESI. So this problem of favoring neutrino masses less than -1 is in fact the same problem that we have in terms of matching omega m's in lambda CDM, of which dynamical dark energy is a possible solution. The whole game of neutrino mass measurements is to try to understand between a normal and an inverted hierarchy. It's very difficult to make inferences when your best fit solution is over in this range of the plot, which is a little bit disappointing. But that's the situation we're in. And there's a whole literature basically discussing this in a very clear way, I think. Okay. This is just the BAO constraints. We have more information in the galaxy power spectrum. And so you might think, why are we not doing like the CMB do, a full fit to the full power spectrum of fluctuations in the galaxy survey? And the answer is galaxy evolution and formation and nonlinear physics. Unlike the CMB, where almost all of the information and a lot of information can be extracted from the linear regime, when you look at a galaxy survey, almost all of the information is contaminated by nonlinear effects. And this causes us problems when we try to fit models to the data. The best models we have at the moment are inspired by effective field theory. They're called effective field theory of large-scale structure. They provide a robust framework for modeling the redshift-based galaxy power spectrum. And they basically extend perturbation theory by having well-motivated extra terms that allow for different parts of physics, including the galaxy formation physics. But what this leaves you is a model that has a large number of parameters. In fact, there are 10 nuisance parameters in total. These are not directly related to the cosmological parameters, but are bias terms, counter terms, stochastic terms that you have to fit. And where you start having this large number of parameters, you start having these prior effects. And we can see this, and you can see this in this collaboration paper, where if we use DESI alone to fit lambda CDM models, in this case, to fit W0 WA cosmologies using the full fit, we're in this situation where the marginalized parameters are very different from the maximum a posteriori parameters. And indeed, if we look in a frequentist sense or we do a sort of frequentist test of these credible intervals, we find that if we do this to MOCs, we get Bayesian credible intervals that are well away from the truth of those MOCs. So we're really being driven in this example by not the likelihood, but the priors we're putting on these nuisance parameters. And in this case, a Bayesian analysis doesn't make as much sense as other analyses. There are ways to get around this. One of them is to use the HOD model to set constraints on the EFT model. So what this paper by a postdoc in my group was trying to do is to basically say, we shouldn't allow all of these nuisance parameters in EFT models. What we should do is constrain them to only have EFT models that also look like HOD models. And this throws out a whole space of EFT models and in fact really improves these projection effects. And that's shown in this plot here. Another thing we can do, which is led by a couple of postdocs in my group, Simone and Marco, and the idea here is that we can rotate the basis of parameters, and we can do this rotation in such a way as to decouple the cosmological parameters from the nuisance parameters. Now, rotating a basis doesn't change the likelihood, doesn't change the posterior, But what the rotated basis allows you to do is to set priors on the nuisance parameters, which are independent of the priors or the effect of the priors on your cosmological parameters. And by doing this separation, you can form a basis in which you can set up priors which now decouple very nicely. If you set up the original priors, you would have the same posterior, but here you can set priors on the nuisance parameters in the EFT model, which then don't impact the end results. And I think this is a really neat way of forming a basis in which it's natural to set priors where you don't really know how otherwise you should set them. So these are the kind of developments happening in the field at the moment to try and get rid of these prior effects in a Bayesian analysis. We are also working on a frequentist analysis as well. If you can get rid of all of these nuisance parameter effects, and you can do it by throwing more data at it, then this full fit gives you a measure of the growth of the amount of fluctuations in structure at present day, which really comes from the redshift space distortion signal in the data. Okay, I'm going to end it there just with a summary. Hopefully, I've convinced you DESI is an amazing experiment. The BAO results are interesting. There are discrepancies with lambda CDM. You can choose your own poison. Dynamical dark energy, systematic data problems, negative neutrino masses, please don't choose this one, large statistical fluctuations. I've tried to give you the full answer, which is dynamical dark energy. I think it's the best theory we have if this discrepancy we see has to be explained by theory. But that doesn't mean that that's the only possible answer. And I've shown you a little bit about full shape results. They currently have limitations, but there are reasons to be optimistic about the future. And at the moment, the collaboration is working on the DR2 full shape measurements to go on with the BAO measurements, as well as a whole range of other science that I haven't talked about at all. Okay, thanks.
I see two questions here.
Hi. Can you talk a little bit about your choice? Sorry, your choice of prior for W naught WA and how that affects your inference.
Okay, so the choice of prior, yes, that's an interesting question. So the prior that we naturally put when we're fitting models on this is a uniform prior in both. That is potentially a source of concern because the W0 WA is just a parameterization of models, and it is basically, we're relying heavily on that parameterization of models. So when we put on uniform prior, we're saying that all of the models in this quadrant are equally likely. But in this case, with the BAO and the CMB and the supernova, we are not in the prior dependent regime. The posterior here is dependent on the likelihood, and that's what's driving it. And you can see this from these kind of plots that show you why that best fit model is favored. So I'm not too worried about this prior on this space. What is perhaps more of a concern would be the prior between lambda CDM and extending the models. So when we say this giving this sigma confidence, that in some sense is a frequentist confidence measure. And people are interpreting it as a Bayesian confidence measure. And if you want to interpret these sigma in a Bayesian sense, in the Bayesian model selection criteria, what you have done is you have put an equal weight on lambda CDM compared to other models in this plane. And some people have argued quite vehemently in the literature that that is not fair. Lambda CDM should have a higher prior compared to other dynamical dark energy models. And that, if you wanted to interpret these sigma in a Bayesian sense, would basically reduce the discrepancy or reduce the preference for dynamical dark energy over lambda. So these are quite subtle statistical arguments about interpreting what we've presented as a sort of frequentist sigma level as a Bayesian level. And then once you've interpreted it as a Bayesian level, you have to bring in a prior, and that prior that you have to bring in has to be uniform for any model in this space. And if you were doing Bayesian model selection from the start, you would probably say lambda CDM should be favored as being a simpler model through Occam's razor over these dynamical dark energy models. So if your question was about priors in that sense, then yeah, that's a really interesting question.
Okay, thank you.
Okay, let's take one more question here.
Oh yeah, I was actually also wondering something on this slide. I was wondering if you could expand a little bit more on coincidence number 2. So I'm kind of not fully understanding why it's a coincidence, because if lambda CDM, kind of 2 leading order, is able to replicate some of the features of the dynamical dark energy model, how is that coincidental?
The coincidence comes about because there is no reason why these models should be preferred, theoretically or otherwise, over a model here or a model here. And if there's a model here, and we looked at what degeneracy all of the data gave, and I had my postdoc do this, we ran a lot of Monte Carlos where we created fake DESI data and CMB data for this model, and we looked at where they were fitted, and they went along a degeneracy like this. And the same up here, they went along a degeneracy like this. So it happens to be chosen, if dynamical dark energy is the solution, that the solution to it goes very close, has a degeneracy direction that goes very close to lambda CDM.
Wait just a second for the mic. Yeah.
As far as I understand it, the preference for omega naught omega A turns mostly because of the low redshift measurement of supernovae, right? Was there, our first question is, are there concerns of that being systematics? And second is that were there tests performed with data splits where you sort of didn't include that lowest point, and did that change things in a significant way?
So the evidence for dynamical dark energy comes from the difference between the CMB and DESI data. So if we use the Pantheon supernova sample, that doesn't actually help us at all, or doesn't give you any further preference for dynamical dark energy. So the dynamical dark energy really is a solution to this problem, where we have different omega M from the different data samples. The fact that some supernova samples enhance this and make the sigma higher, 2.8 down to 4.2, comes from this low redshift data point here from DES, from Union 3, but not from Pantheon.
Okay, go ahead, thanks.
All right, so let's break here, be back at 10:10 sharply, and thank you, Will, once again for the wonderful set of lectures.
I know you don't like the coincidence.
It's an RFQ.